Hi, my name is Jacob Lacey, and today we're going to be looking at this E&M problem. So the question says, a very thin spherical shell with radius r has a charge density of sigma that depends both on theta and phi of a cosine theta, where a is a constant. You may notice that there's no phi in this equation for the charge density. That just means that in the phi direction, um, it's uniform, and that's going to help us later when we have to integrate. And we also need to find the electric field along the z-axis for z less than the radius and z greater than the radius. So I kind of drew out the problem a bit, the thin spherical shell, and trying to solve for the first part, z less than r. If you notice the word very thin, inside the sphere, there's going to be basically nothing. So you can think of it as sort of like a conductor, or in other words, that inside the sphere, or z less than r, that q enclosed is equal to 0. And if q enclosed is equal to 0, that means E, electric field, is also 0. So that's for z less than r. It's a bit more tricky for z greater than r. And we can't use Gauss's law because Gauss's law applies to a uniform charge, and our charge depends on sigma, and that sigma ranges between the angle theta. So we can't use Gauss's law here, but we can use this equation. We can use electric field, which is a vector, is equal to 1 over 4 pi epsilon naught, and it's the integral of sigma as a function of r prime, which r vector prime, which isn't going to really matter since this is going to be the same as that, over the magnitude of script r cubed times our separation vector script r times dA prime. So this is what an equation that we can use to solve for electric fields for v greater than r. But in order to do that, first, there's a couple things we got to know. So we need to know the field point, or just r vector, the source point, or r prime vector, the separation vector, script r, and the magnitude of the separation vector. And I'm just going to draw down here since I take forever to write. So that's just that. And lastly, you just need to know dA prime. So for the field point and pretty much everything in here, if we take the sphere that I drew earlier and change it into 2 dimensions, keeping the z-axis on top, and it doesn't matter for x and y, since the sphere it's going to still be a circle, and it's not going to matter either for x and y. It's not going to really change our equation, but I'll just say X for this case. So our field points, since we're looking for the electric field along the z-axis, it's just going to point straight up at a distance z, and it points in the z-hat direction. So we know the field point is going to be z times z-hat. For the source points, it's going to be along the radius, and it's just going to point in the r hat prime direction. So it's a length r, and it's varying with r hat prime. So we know the source point is going to be r, big R, r hat prime. And the separation vector is just defined as this field point minus the source point, r vector minus r prime vector. And we already know the field and source points, so that's just going to be z minus z hat, z times z hat minus r hat, right? And the magnitude, noticing this angle, magnitude is usually like, or think about it as like the finding like the distance there, and this angle is not perfect 90 degree at all the time, so it depends on a cosine theta. You can think of it as like an extension of Pythagorean's theorem. So we're going to use law of cosine here, and this is just going to become the square root of z squared, which you can think as the x or the y distance, and big R squared as the x distance. And law of cosine just means that this is going to be 2 minus 2z r cosine theta. Okay, so dA prime. So we know that it's not changing in the r direction, and we're dealing with an area, so it means it's changing in the both theta and phi direction. And since we're in spherical coordinates, we also have to include r squared sine theta. But in this case, our little r is just big R, so I can rewrite that as that. And lastly, we should probably know where theta and phi are changing from. So theta is ranging from the top z-axis up here down to there. So it's going from 0 to pi, and phi is the angle along the xy plane is doing a full circle, 0 to 2 pi. Okay, so we pretty much have everything that we need. Now we can set up our integral. So this integral is going to turn into a double integral, since we're dealing with two changes. So I should also mention, so this is going to be in the EZ direction, or they call this E subscript Z, meaning that E subscript Z, and this is going to help because we wanted to have like no vectors. And this is, we want to find the electric field in the Z direction. So this is electric field dotted with Z hat, meaning wherever we see in a vector, in our case, it's just the script R, the separation vector, we multiply it, or we take the dot product, not multiply. So Z dotted with the separation vector. So Z hat dotted with the separation vector is just, given that our separation vector is this over here, it's going to be Z hat dotted with Z hat minus r hat prime dotted with z hat. So z hat dotted with z hat is just 1, so that cancels. And r hat prime dotted with z hat, if you go back to the circle drawn over here, you'll notice that they make an angle, and that r hat and z hat both have a length of 1, so it's just going to depend on an angle, cosine theta. So this whole thing just becomes r z minus r cosine theta. So back to what I was saying over here, now we can just integrate ez without any vectors. So we set up the integral 1 over 4 pi epsilon naught integral from 0 to pi, and the integral from 0 to 2 pi. And so we know sigma is just a cosine theta. And that separation vector just turned into z minus r cosine theta. And now we just have the dA prime, which is just r squared sine theta d phi d theta all over the magnitude of the separation vector cubed, which is z squared plus r squared minus 2zr. Write that a little bit better. To the power of 3/2. So the first integral, if we just, since it's not changing with phi, we can pull everything out. Now we're just integrating from 0 to 2 pi, just d phi, which is just multiplying by a 2 pi factor. So we can put that in front. Also, we can also pull out a and pull out r squared, meaning that this integral simplifies to e over z 2 pi over 4 pi. Wrote that first to show that that just simplifies to 1/2. So you have 1/2 epsilon naught. And on top, a times r squared. And now this is a single integral of 0 to pi. We multiply that cosine to there and there. We get z cosine theta minus r cosine squared theta. And then in parentheses, sine theta d theta all, oh, I made a mistake here. There's should be a cosine theta here. All over c squared plus r squared minus 2zr cosine theta. to the power of 3/2. So this is an ugly integral. It's not really a way you could solve it. There is a way you can, I guess, simplify it. So I'll simplify it. We do a u substitution and let u equal cosine theta. And du, the derivative of that would be minus sine theta d theta. And if we change our limits of integration just by plugging in pi and 0 from our limits up here into cosine, that means u is changing from -1 +1. And so as simplified as this gets, we find that EZ is equal to minus a r squared over 2 epsilon naught. And integral from -1 to 1. Z times u minus ru squared du over z squared plus r squared minus 2zr u, all to the power of 3/2. And like I said, this is not a nice looking integral, so yeah, this is probably as simple as it gets. And this is what the electric field in the z direction would be for E greater than R. And like we did earlier, we got the integral, we found out what the electric field is for Z less than R. So those are the two electric fields for that, and the problem is solved.